Recording is rolling. So welcome to Thursday, September 16th. I'm starting you guys off with a couple of free body diagrams. You might remember yesterday, I was taking you guys through some PowerPoint slides that involved a bunch of free body diagrams. We did quite a few of those. I also gave you guys some additional notes on friction, and there are different kinds of forces. So today I'll eventually tell you guys about Hooke's law and spring force. So we're going to build up to that point though. So for now, we've got, can draw a free body diagram for a car braking to a stop. And actually I got two slightly different scenarios. The one on the left says the driver brakes, the wheels lock, and the car skids to stop. And the one on the right, it says the driver brakes, but this car has ABS, anti-lock braking system, which prevents the wheels from locking. The wheels actually roll a little bit and the car comes to a stop. Did you guys, when you got your driver's licenses, have to learn about anti-lock braking systems? Yeah? Yeah? Oh, I heard some no in there? Yeah. I've been asking this question all day, and I've been getting a mix of yes and no on this. So, well, I'll tell you guys what the physics of this is. The physics is that, you guys remember from yesterday that there's actually two different kinds of friction? I was telling you guys there's what's called kinetic friction. That's like sliding friction. Two surfaces are sliding past each other. But then there's static friction, and that's it before you break the initial friction. Remind you guys why the static friction has an inequality versus kinetic friction is an equal sign. Because, here, we'll do this right here, do a live demo. Got the spring scale measuring how much force in newtons. And notice that, ooh, look at that. For the first few newtons of pulling, this weight right here is static. See how it's not moving at all? That's true for, get back up here. Like half a Newton, 1 Newton, 1.5 Newtons, 2 Newtons. See, it's over 2 Newtons now and nothing. But during those first couple of Newtons, right, see how it's like building up? That's why it's an inequality for the static situation. Now, once it gets sliding, it just stays, I can pull at a constant force for constant speed. And remind you guys too, we put together this graph, say what's the sliding speed between two surfaces? What's the resulting coefficient of friction? Well, before it breaks the friction initially, it's a large value, static friction. But then once the two surfaces are sliding, it doesn't matter what the speed is between these two. It's pretty much a constant value, and that's called kinetic friction. Now that I should say coefficient of kinetic friction. Now the coefficient of kinetic friction, remember what coefficient of friction is. It's defined as the ratio of friction force to normal force. It's that ratio. So that's yesterday's notes. Sure, here, good. Right. Right. And the fact that static friction is more than kinetic friction, that would actually be a better friction to take advantage of, wouldn't it? Go back and look at this graph. Like if you could take advantage of static friction, which is always more than kinetic friction, then you could stop sooner, couldn't you? Now, this coefficient of friction is a material property. In the case of cars coming to a stop on a road, we're talking about whatever the friction is between rubber tires and an asphalt road. It's going to be like some number. Well, it's actually two different numbers, right? It depends whether it's skidding or not. Now, if you're in an old 1970s car, like this one on the left, then the wheels will lock, right? And the old advice used to be this. Now, what I'm about to say, do not do what I'm about to say. But if it was many decades ago, you would have done this, which is that you weren't actually supposed to slam the brakes to come to a stop. If you wanted to stop in a hurry, what you're supposed to do is like pump the brakes, kind of like ease on them, on and off. Right? That was the old advice. That's not the new advice. The new advice, if you buy a 21st century car, it'll have anti-lock braking in it, and you're supposed to go ahead and slam the brakes, and the computer system will automatically do the pumping for you. So it will prevent the car tires from locking. It'll actually roll them ahead a little bit, but the fact that the car tires are rolling a little bit, it gives them more traction with the road, you get more friction, and the car comes to a stop sooner. Okay? So that's the physics behind that. But let's look at the free body diagram. So how would these two diagrams compare? So you guys remember free body diagram, FBD? That's what FBD stands for, right? Free body diagram. You only label what kind of force, or what kind of vectors? Force vectors. You don't care about velocity vectors, anything like that. Right? Now, if velocity is important at all, it's just to tell you the direction of friction, which always opposes that. Okay? So let's do the one with like sliding, like old 1970s car versus the new anti-lock braking system car that can take advantage of U sub S. Okay. let's say the computer system adjusts to take like full advantage of that mu sub s. So it goes all the way to the maximum possible value. Something like that. Okay. Okay. Did you guys draw on each of these cars a weight pointing straight down? And you label that mg because mg is weight. AP also accepts f sub g. Well, I'll make a little note here, f sub g. Okay, but I prefer mg because I've just done that all my life, so I'll use that. Okay. So let's say this other car, the new car, has the same mass and the same weight. So that's the same so far. No, if you stop there and you walked away from the paper, then you would be saying that those cars are doing what? Free fall. Right? Maybe they drove off a cliff like flying off, like all dramatic, probably into a giant mushroom cloud. But that's not what's going on. There's a road that's holding up at each of these cars. There's a road. Okay? And that's providing a what kind of force? Normal force. You guys remember this? Normal force. So this is F sub n, which is the normal force. And what does normal mean again? If two lines are normal, they're what? Perpendicular. So literally, the name of this force is the perpendicular force. Perpendicular to what? The surface, right? Remember if you have a surface? Right? Now, in this case, we're doing pretty straightforward. It's just a level surface, horizontal. Therefore, the normal force is straight vertical, but it's like perpendicular. Okay, so we've got a couple forces. So far, it's the same free body diagram for each one of these. Okay. Free body diagram. Okay. But now we need to bring in the friction force. Now, here's where there's going to be a difference. Now, I just made up some coefficients of friction, but just to get the point across. Let's say the coefficient of kinetic friction, mu sub k, is 0.5, and the coefficient of static friction is 1.0. Okay? Can you guys draw proportionally correctly what the friction force looks like for each one of those scenarios? So if mu sub k is 0.5, that's not part of that vector. That's just off in the ether. Versus 1.0. Two different coefficients of friction. Remember, coefficient of friction is the ratio of friction force to normal force. And notice I did not put a unit on that coefficient of friction. You guys won't deal with very many unitless values in this class, but that's one of them because it's newtons per newton. Okay. So here's how I would draw the coefficient of friction for the sliding car, old 1970s car. There's the friction force. Okay. Notice how I made it about half the magnitude of the normal force. See how that divided by that is that's a 0.5 ratio, isn't it? Like 1 over 2, 0.5. Okay. Like that's why 0.5. Okay. And how about the one with the anti-lock braking system? What does that friction force look like? Yeah, the same magnitude as the normal force. Look at that. See how that and that have the same magnitude? The friction force and the normal force have the same magnitude? Right? Because the coefficient of friction is a 1-to-1 ratio. Right? Right? Guess that? That's coefficient of friction. Right? Good so far? I want to go one layer deeper. I want to connect this back to the kinematic motion that you guys started learning about. Because you guys know car braking to stop, that would be an accelerating situation, wouldn't it? Each of these cars has a net force, which means that they would be accelerating. Accelerating, I'm using it in the physics sense. It could be a rate of slowing down, which these cars are doing. They're slowing down. So I'm going to bring up Newton's second law of motion. F equals ma. Now, I really prefer the version that's the fraction version. Acceleration is a net force divided by total mass, but this will look a little bit cleaner in my notes. Okay? Now, you guys know this is talking about a net force, right? Net force results in a mass accelerating. Okay? I wonder what rate this car can slow down. That's to say, I want to solve for acceleration. So once you know acceleration and you know all that kinematic stuff from the first few weeks of school, you can put 2 and 2 together and figure out, I wonder what the braking distance is going to be, how much time it's going to take, if you want to know any of that stuff. Okay? Hey, what is the net force on either one of these cars? It's which one of these? The friction force. Because don't the weight and the normal force just balance out? Okay? As long as it's a level road, nothing crazy going on. Yeah, this and this tip to tail, zero out. There's no vertical force net. Well, there's no net vertical force. There's 2, but they cancel out. The net force is the friction force. This right here, for this scenario, is the friction force that's causing the car to slow down. Right? Oh, but you know what else? The friction force, you guys know, is equal to coefficient of friction times the normal force. Is that true? So we can relate the friction force back to the normal force, right? Everything goes. Think about this line version of it, right? So couldn't I take this and I could do another substitution? I could say that's coefficient of friction. Now, if we're doing the anti-lock braking side, this would be static friction. Okay? Also, I'm making an assumption here that the computer system is maximizing that value, because remember, otherwise it's an inequality. So let's say we're taking full advantage of the maximum possible value. So that'd be times the normal force is equal to the mass times acceleration of the car. Okay, so now we're getting one step closer. Oh, and the normal force is equivalent to what? Yeah, the weight of the car, mg. So I can do another substitution. Say coefficient of friction times mg will tell you mass times acceleration of the car. And there's a reason I'm making all these substitutions, because at this line right here, what do you guys see is going to happen to both sides? Mass cancel, which is a pretty common thing to happen in this class. Right? It's happened quite a few times before. And you guys know when a variable cancels in physics, it means that the magnitude of that thing doesn't matter. Okay? So for example, say we got an empty car. This guy drives to the grocery store. He's in a hurry. He's breaking all over the place. Right? Then he fills his car with groceries. Like, I gotta get ready for the next pandemic. Need all toilet paper. He drives back to his house. The fact that his car is like loaded with groceries, is that going to affect the stopping distance when he brakes? No, because the mass canceled out. Or here's another classic physics 1 question. Let's say you have two vehicles side by side. One's a little tiny sports car, one's a big old semi-truck. But otherwise, all else is equal. They've got the same brand tires, they're driving on the same road, they start at the same speed, they brake at the same time. Which vehicle, the little tiny sports car, the big old semi-truck, is going to stop first? According to this, they tie, right? It takes the same time and the same braking distance to come to a stop because they slow down at the same rate. Okay. So the last line here, I'll say the slowdown rate is just equal to coefficient of friction times gravity. Okay. The mass of the car canceled out. Oh, yeah. Listen.
I understand how it works with the formula, but like in real life, how does that work with like the whole inertia thing? How does something like? Right.
Yeah. It's true. The semi truck. Yeah. So if you try this out in real life, would it exactly work like this? And so there's some simplifications in this class. Like one of our simplifications is like there's no air drag for a big part of the class. Okay. So would it work out exactly like this? Probably not exactly, but this is probably a pretty close model, and it's off a little bit. You're right. The semi truck would have more inertia. Now, if you go back to just the textbook version, like a paper version, it has more inertia, has more mass, but that means it has more weight, which means it has more friction force, and then it just ends up canceling out. So, yeah, that is true. Oh, yeah.
Would the truck not need stronger brakes than the car, though?
To
help cancel out that inertia?
Right. Yeah. So, what about the brakes? Would the truck need stronger brakes? Right. Well, there would be a greater friction force, right? So, because more normal force, because more weight on the truck. Yeah, so I think it would need stronger brakes because there would be more friction force to slow it down. That's true. Yeah, so you need that. Okay. Now I could do the same math with the 1970s car over here compared to the ABS. So I'll just do ... It's the same math and get the slowdown rate is equal to coefficient of kinetic friction times gravity. It's the same story. Okay. Is that? So there you go. Now you guys can figure out a kinematic value of its motion, based on the dynamics of the forces. The reason I definitely want to bring up the sports car and the semi-truck is because, well, first of all, it's a really classic physics question. And AP could definitely ask that question, and they would expect to see something like this written out, and then the mass cancel out, and they say, same talking distance. Okay. All right, gonna flip my screen over, see present screen to share. Right, and let's pick up on this PowerPoint. So I'll flash through the first few slides just to cue you guys back into physics. If you're coming from Spanish, like, what's going on? So remember, free body diagram, we're looking at force vectors and only force vectors. And there's a certain convention to draw these. So connect each force vector to the center mass dot. AP is really strict about this rule. So if you draw force vectors like floating out in space, even if it could explain the situation, they will give you no credit for that. Okay, force vectors measured in newtons. Do you care about velocity vectors for free body diagrams? No. So sometimes we'll give that for context, but that's not actually part of the diagram. Block at rest on table, weight down, normal force up, boom, done. Block at rest on table, but what if you're pushing it, but it's still at rest? So you're pushing it, but there's a friction force that's building up, just like I showed you guys with the spree sail where it's like stuck. What if you're pushing it so that it moves at constant velocity? Ooh, constant velocity. Do you guys notice that this free body diagram is exactly the same as the previous one? In fact, if all you had was the free body diagram and you did not know if this was static or kinetic friction, it would be ambiguous as to whether this block is even in motion. Okay? But that is consistent with a question I've been asking you guys all along this class. If you're in the passenger seat of a car and you're blindfolded, can you feel the motion of that car? Can you feel how fast it's going, I should say? Is it going 60 or 70 miles an hour? No, because velocities are relative. We can't feel the Earth spinning right now. For all we care about, we might be at rest, right? And for thousands of years, people thought we were. Can't feel velocities. Okay? Block on table, push horizontally so that there is a net force. Well, there's one possibility. Right? See how there's a net horizontal force? Okay. Rocket free fall, boom, done. Its own weight is the only force on it. Okay? And if you want to know what is the acceleration, just take that net force and divide by the mass. Oh, you would get exactly g, wouldn't you? Right? 10 meters per second squared. What if there is air drag? Ooh. Now, is that rock accelerating at 10 meters per second squared anymore? Yeah, it's probably closer to like 5 meters per second squared because the net force is less than its own weight divided by its mass. Now, here's where I had you guys also. Where's this graph from yesterday? Oh, here it is. Here. I had you guys. I talked a little bit about air drag yesterday. So I gave you guys a bonus equation that is not going to show up on AP, but just give you guys some context so you can think about how does air drag work. Okay? I mean, it's related to cross-sectional area, which is good news for this guy with the parachute. That's why you brought a big one with him. Okay? Take advantage of that. But also this. So the faster you go, the more the air drag builds up. So, and I had you guys draw a graph. What would the V versus T look like? Now, the classic V versus T that we've been doing for kinematic motion is just this, like a straight line with slope G. That's without air drag. If you include air drag, remember that at the beginning, it's not going to be very much air drag, so it's not going to be a whole lot different from the frictionless case, from the vacuum case. Okay? But if it falls for long enough, that air drag is going to build up and up and up until it eventually exactly matches the weight of the object. And when it does, that object has reached a state of what? Yeah, terminal velocity. It's in equilibrium, right? All the forces are balanced. Terminal velocity. And on a V versus T graph, that shows up as a horizontal asymptote. And we'll do that. It'll go constant speed all the way down, which will be different values for different objects. Hopefully for this parachuter, this is like really low on the graph so that he hits the ground at a really low, small speed. Okay? So back over to presentation. Oh, nope. Hold on. Gotta fix this. All right. Flip that screen. Exit this. Okay, exit that. Okay. Okay. Hit flip back. And present. All right, and we're back. Okay. So the next slide is what if it actually does reach all the way up to terminal velocity? That's that right there. Now it's in equilibrium, so it'll go down constant speed all the way down. Okay. But moving through water, constant velocity, all the forces balance, vertical balances, horizontal balance. I give you guys a challenge question. Can you do 3 vectors that are in equilibrium? There's 2 possible solutions. Parachuter before terminal velocity, parachuter at terminal velocity. And then this is the last one you guys saw yesterday. You guys remember this? Rocket just screaming through space, constant velocity, 10,000 meters per second. What was the answer to this one? Yeah, that. You guys are looking at the answer. There are no forces at all. Then how's it in motion? Because of its own inertia. That's it. Inertia is just keeping it going, right? Just like the Voyager spacecraft. See, if it turns on its engines, then it would have to speed up, wouldn't it? Because there would be net force. Then it would no longer be constant velocity. All right, so new stuff. Air hockey puck moving across the surface at constant velocity. Let's ignore the fact that it's being pushed against a little bit of air drag. So air hockey puck. Whenever I'm going to walk around the room. I wonder how many guys are going to get this free body diagram. This one's a little tricky. I have a handful of students each class have been able to get this one right. So air hockey puck or air hockey. You guys have all played air hockey, right? I'm going to use that as a proxy for a zero friction situation, which actually is a really good model for it. It really is approximately that. So air hockey puck is going constant velocity across the table. Oh yeah, Sammy got it immediately. Wow, that was very fast. Yeah, Eddie got it. I got 2 winners already. Eric got it. Okay. Yeah, Stefan got it. Who else is gonna get this? Grace got it. Mauricio got it. Not quite. Alyssa got it. And Deacon got it. All right. Yeah, I got a bunch of winners. Yeah. I think the kids are getting smarter every year. I don't know how, but you guys are like looking up physics stuff online or what? But somehow you guys figured it out. All right. This guy, it's got a weight pulling down. It's got the force from the air jets holding it up, kind of like a normal force, right? And that's it. That's the whole free body diagram, right? Again, if all you saw was the free body diagram, you wouldn't even know if that was in motion or not, because again, all velocities are relative. So it would be ambiguous as to whether it's at rest or in motion. Yeah. So free body diagram, you only care about the forces.
So like, I mean, it says it's moving across. That means it had to be hit, right?
Yeah.
Not a force being put on it.
Yeah. So if you go back to this situation, like if I said, the situation was like you're hitting the air hockey puck with the what do you hit it with? What's that thing called?
Puck.
Well, okay, the puck.
That's the puck.
What's the thing that looks like a looks like okay. Anyways.
I like
The red circle.
Yeah. So if you were hitting it, then yeah, there would be like a push hitting it. But just like in this class, so like if you throw a ball off the edge of a cliff, or if a cannon shoots a cannonball, we only care about like starting with the moment right after that.
Okay.
So yeah, same thing here. It's in motion. It's going constant velocity is the key. So if you put a horizontal force on this, then it would no longer be constant velocity. The Earth and Moon. Here's a good one. Guys, is the Earth pulling on the Moon?
Yeah.
Yeah, that's pulling in an orbit. Is the Moon pulling on the Earth?
Yeah.
Yeah, that's why there's like tides and stuff. Okay. But which force is bigger though? Same force. I almost tricked you guys. Almost. Yeah, it's the same force, isn't it? Same force. Okay. Do you guys draw that right there? Earth on Moon, Moon on Earth. Right? No, hold on a minute. Is it really the same force? Because the effects are completely different, aren't they? Like maybe the Earth wobbles a tiny bit, but the Moon is like in orbit around the Earth. Right? That's a drastically different acceleration, isn't it? Because those two objects have different what? Masses. Yeah, the Earth is so massive that force barely moves it, but the Moon has such little mass that it accelerates a lot more. It's a centripetal acceleration in that context.
That's the one thing I never understood is like orbits and stuff. Like,
yeah,
why doesn't the Moon just crash into the Earth? Why is it moving in a circle and doesn't just get pulled? That's what
that is. Yeah, why doesn't Moon crash down to Earth? That is Unit 3 of AP Physics. So we're gonna study that pretty soon. That is coming up.
Okay.
All right. So for now, I do want to convince you guys that the forces are equal, right? Because that might not be immediately apparent. Like Newton's third law of motion is one of those that everybody can say the words, but how many people like intuitively can grasp this and understand this? I'm going to represent each mass with one of these guys, or plastic kilogram. So represent this mass with a kilogram, so a little hook on it, and same thing. Okay. So let's say we got a planet and the Moon, but maybe they're like the same mass. Okay. If they were the same mass, then they would definitely be pulling with the same force, same gravity force, right? So you got force this way, send that a little bit. Okay, that's probably pretty close magnitude. Okay, gravity force like that. Okay, but the Earth, of course, is much more massive than the Moon. So I'm going to represent that by just throwing in more lab weights. So as I increase the number of lab weights, that's representing like more and more mass, right? Let's say you had a planet that's like 3 times the mass of its Moon, something like that. Like 3 lab weights compared to 1. Wouldn't these new lab weights also pull the Moon lab weight like this? So this is pulling this way, this is pulling this way. This one's pulling this way and this way. Like that. If you didn't see it before, I bet you definitely see it now. Look, 3 units of force this way, 3 units of force this way. See how no matter what, even if the masses are different, see how the forces have to be equal? Yes, yeah. I actually stole this idea from, do you guys know a YouTube channel called Veritasium?
Yes.
Veritasium? Yeah, I do recommend that if you got some spare time and want to find a good YouTube channel called Veritasium. It's a really good science channel, so yeah, that's one of his old videos there. Hey, I flipped back and it didn't mess it up. All right, crossing the Ford and Oregon Trail. Sometimes you get across. Roller coaster, top of a hill. We're going to do a few roller coasters. Now, this one is super basic. Let's just say the roller coaster one. It's basically 0 velocity. You think there's a weight down and the normal force from the track holding it up, and then that's probably it, right? Something like that. Okay. Now notice I didn't. Okay, so that could be that one. Next one. Let's say this roller coaster crashes down into this valley. And I did draw a fat velocity vector, not because it's part of the free body diagram, but it does influence the free body diagram. The fact that the roller coaster is in motion. Now, this one's pretty tricky, and some new concepts are going to open up that I haven't talked about yet. Do you guys remember if you're in a car, there are 3 controls where you can feel something happening? You can slam on the gas pedal, you can slam on the brake. You can also do the steering wheel. I said, we'll eventually bring in the steering wheel. Well, we're starting to kind of bring that in here. So this is going to be a new concept, like going around a curve. That there's some net force or some kind of acceleration involved in that. What are these forces going to look like? Did you guys put a weight on that coaster? So it's got a weight down. Okay. Is there a normal force from the track pushing up? Okay. But before I show you the normal force going up, once you guys can get this exactly right. Okay. So the fact that this roller coaster is in a curved part of the track and it is in motion. As it moves forward, it doesn't actually go straight forward. It actually isn't overall going to be forced upward, right? So which way do you think the net force is on that roller coaster right there? Has to be up, which means the normal force is scaled how compared to the weight? Yeah, it's greater. It's greater. Yeah. Yeah.
Is this the same as that example you gave when you like drop something onto the ground, its acceleration actually goes the opposite direction for a moment? Is that what's causing that normal force to be greater?
Yeah, what's causing the normal force to be greater is that, see, like the force from the tracks, if the force from the tracks were the same as the weight of the coaster itself, that could be okay if it was a flat track, kind of like the car on the road. Right? So weight down, normal force up, it balances, all good. It can just go in a straight line. But if this car is being forced into a curve shape, then it's being forced to change its direction. So it has to overall be accelerated upward. Okay? And the only way to do that is, well, there has to be a net force upward. So the upward force has to be more than the downward force. Kind of that. I don't remember the example you mentioned. I don't know that. So.
No, I was thinking like, you know how when you drop something and it hits the ground, that's acceleration in the opposite direction. When it impacts, like braking, acceleration back.
When it impacts it?
That might
maybe. Yeah, I guess that could kind of be related, right? If something's like changing direction, right? Something like that, right? So, yeah, if the ball bounces on the floor, yeah, it would change direction at the floor, so it would accelerate upward during the bounce. Yeah, and then, yeah, similar idea here. It's going to overall accelerate upward. You guys cover that? Okay. We're going to do one more roller coaster, and this last one is probably the trickiest one. This one I'm going to walk around the room and check and see how many guys get this. All right. So say this coaster keeps rolling. I'll give you guys some context while you guys are thinking about this, give you guys a head start. So this roller coaster is going around the loop, and now it's at the top part of the loop. And I did definitely specify that this is in motion, because if that coaster were not in motion, wouldn't it just want to fall right off the track, which would be bad news for, well, everybody inside it. Yeah, oh yeah. But this thing is in motion. It's hopefully going to get around the track. I bet it. Do you think there's some minimum speed that would be required to get around a track? Say if you knew the radius of this loop, I bet there would be. There'll be something that's a future topic. Right? And actually, you could even do another step. Do you think that there's some minimum hill height? See, remember this was falling from a hill. Do do you think there could be some calculatable minimum hill height that could allow it to have a tipping point speed where it could just barely get around that loop? That'd be true too. That's also something that I'll have you guys solve in the future. But for now, let's just focus on the free body diagram. Let me glance around the room. I wonder how many guys got this one. This is a really tricky one. Start on this side. Not quite. Good guess. Oh, Breezy got it. Who else gonna get the? Oh, yeah. Abba got it. Abba got it. Got it. Juliet got it. I got 3 winners already. That's great. Oh yeah, Nick got it. Mauricio got it. Lavanya got it. Almost. And, all right. Wow, had quite a few winners. Yeah, hardly anybody gets this, and I had a bunch of winners in here, so that is awesome. So you think the weight of this is trying to pull it off the track, pull it straight down? Okay. Do you think there's probably also a normal force from the track? Probably so, but that track is pushing the cart which way, up or down? Down. That's it. That's the answer.
What?
That's the free body diagram. Yeah. So now, if you're along for the ride, if you're inside that coaster, maybe you're blindfolded. It feels like there's a force which way? Maybe, yeah, upward. It feels like there would be an upward force. Now, there's a whole conversation about this we're eventually going to go into, but that apparent upward force is only sort of true in the context of a rotating frame of reference, like if you're along for the ride. That's called centrifugal force, which literally means center fleeing force. But tell you what, too, that term centrifugal force is like nails on a chalkboard to a lot of physics teachers, because from an inertial frame of reference, that's to say from our point of view, looking at this from the side, it does not exist. There's no such thing as any kind of force going upward. There's only a centripetal force, which is the sum of the, well, in this case, the normal force plus the weight that's pushing it down. See, as that coaster is moving to the left, it's also being forced down into a curve. And all the forces the only forces on it are both pushing it down. It's weight trying to pull it down, but the track itself is also pushing the roller coaster down. Now, if you only show the weight going down, that would actually be the case where it's just barely getting around. Like if you take this normal force and make it less and less and less until it approaches 0, then you would actually be setting up a situation where it just barely gets around. You could solve for the speed that would just barely get it around. So there you go. Awesome if you got that. Oh, hey, car brakes just up. We did this one earlier today. This car has a weight. This car has a normal force and a friction force that opposes the motion. Boom, boom, boom. Now, who can look at that free body diagram and get a pretty good ballpark estimate of what the coefficient of friction between the tires and the road are for that car? 0.5 is a pretty good guess. And you guys get it by taking the friction force divided by the normal force. See how that vector is about half of that vector? That would be a 0.5 ratio, wouldn't it? Coefficient of friction. Okay. Car goes around a curve, is seen from behind. Let's say we're looking at the taillights of this car. So steering wheel is going on. There's a weight pulling down. There's a normal force holding up. Remember, we're looking at the taillights of this car. Now, why is it going around the curve? I was ambiguous about that. So probably one of 2 reasons. Either the road is banked. Now, if the road is banked and AP asks you this question, then here, I'll tell you exactly the answer they're looking for. They would be looking for the horizontal component of the normal force from the road. Okay, that's what would be setting it around. Okay. But if the road is flat, then there is no horizontal component of a normal force, right? Okay. If the road is flat, what force is setting it around the curve? It can't go around a curve unless there's friction, right? If it's an icy road, you'd have a really difficult time turning, wouldn't you? Right? So there's a friction force. A block hanging at rest from a spring attached to a ceiling. Oh, okay. Do you think there's a weight pulling that block down? Yep. Do you think that spring responds by pulling back the other way? Yep. How did I know to make this the same magnitude? At rest. Right? At rest is one example of equilibrium. Let's go and recap that too. Guys, does equilibrium necessarily mean at rest? No, you could be moving at constant velocity, and that would also be equilibrium. Just all the forces have to balance and there's no acceleration. But at rest is definitely equilibrium. So here's where I want to flip the screen and give you guys some notes on this one. So when we're talking about springs, I'm going to talk about Hooke's law. All right. Hooke's law. Let's go here. Hooke's law. Okay. So Hooke's law says, some textbooks write it this way: the force from a spring is equal to negative kx. Okay. And you tell you what all these little bits mean too, but I usually write Hooke's law this way: force on a spring. Well, that would just be the equal and opposite force. So then you can just drop the negative sign and say kx. But what the heck is k? And what's going on here? Now Hooke's law applies to an ideal spring. So this is for an ideal spring. An ideal spring just follows Hooke's law. That's pretty much it. Okay. We draw this out and then tell you what x and k are from a picture. So you have a very long ceiling, very wide ceiling. Maybe we'll do like a before and after picture. Okay. So before, there was a spring that was just hanging there, and it maybe has no force on it. It's just hanging and has some kind of natural length like that. But now let's take a lab weight and attach this lab weight to it. It's gonna pull it down. It's gonna stretch it. Now, the more you stretch it, isn't that spring gonna pull back? Maybe it stretches it to like right there. Got a big old mass on that thing that has some weight, and that weight is actually pulling. Because weight's a force. Right? Look at how much it stretched it. From there to there. So that amount of stretch, I'm going to call x. Some textbooks say delta x. Maybe I should write that in the margin here. Let's say, or delta x. Delta x meaning a change in length, right? Delta x. And then you could write Hooke's law of F equals k times delta x, but let's call it x. Okay. So remember, this one on the left is an unstretched spring. And then the one on the right, of course, is a stretched spring because there's a weight on it. There's a weight down, mg. Okay. Something like that, mg. And of course, the spring force pulling up. F sub s, spring force. So x represents how much the spring is stretched. Or, you know what? It also could represent how much it's compressed. So I'll say, or compressed. Because you could also push on a spring and compress it, couldn't you? Like squash it. Okay? Either way, this will work out. What is this k? This k, well, you guys have been stretching some springs earlier this week. You guys have some spring scales, and these would measure some kind of force. And remember how, like, the green spring, a little tiny force, stretch it real easy, but the gold spring, it's like super stiff. Hey, that stiffness. Do you think that's what that k represents? That relates how much it stretches to the force, right? So that k is what's called the spring constant. And think of it like stiffness. Like, how stiff is that spring? Not very stiff for the green spring scale, but really stiff for the gold one. Can you guys draw a graph for Hooke's law? Graph for Hooke's law. So I'll put x in meters on the horizontal axis. I'll put force in newtons on the vertical axis. It could be, now if it was not stretched at all from its natural length, that'd be 0 stretch. and that would require 0 force to do that. So there's that point. I'm going to use this boxed in version that I wrote. Well, we talk about tension and compression. We go back and say, well, why do some textbooks like this negative sign? Now, if you include the negative sign, you're doing it from the spring's point of view, or what are you doing? Yeah. What's the force from the spring? Okay. So, for example, if you stretch it, isn't the displacement in this case down, and doesn't the spring force pull back up, which is the opposite direction? That's why negative, right? Or if you compress it, you'd be pushing one way, and the spring pushes back the opposite direction. That's what the negative is about. But if you did the other point of view, like force on a spring, you just keep positive. Did you guys draw that graph? You guys know what that graph looks like? Did you guys come up with that right there? Okay. Where the slope of this line is what? K, the spring constant. There you go. F equals Kx. That looks a lot like y equals mx, doesn't it? F equals Kx. Okay. And notice that you're actually allowed to take this line into negative territory. It could go like past the origin point, because one way would be stretch and the other way would be compressed. So this might be how much it stretched, and the negative territory would be compressed, and then the force would also reverse. Okay. Good. Let's I've got these spring scales broken out, and I'm talking about how these scales have different stiffnesses. Let's do a quick demo and figure out, I wonder what the spring constant is in each one of these spring scales at the least stiff and the stiffest spring. Let's find out. So, divvy this paper in half. What is the, we'll do for the green spring scale and the gold spring scale, which I've chosen because those are the two most extreme spring scales, but coincidentally, these are also our school colors. Yay! So we're using Hooke's law, F equals Kx for each one of these. We're solving for K. F equals Kx. Solving for K. Now, let's start with the green one. Did you guys notice, this may have been so obvious that it just slipped your mind, that the spring scale is scaled linearly? So it goes 1 Newton, 2 Newton, 3 Newton, 4 Newton, 5 Newton, and each Newton is about a centimeter apart, scaled linearly. That is exactly consistent with this graph being a linear graph, right? Force versus how much it stretched. Right? Actually, it isn't exactly a centimeter, it's pretty close. So to pull up to 5 Newtons, that maxes out the green scale. 5 Newtons, let's see what distance that is. It's actually 5.2 centimeters. It's 5.2 centimeters. Okay. So for 5 Newtons of force, we're solving for how stiff is that spring? Okay. It's 5.2 divided by 100 meters, right? The centimeter, you guys know, like 100 cents in the dollar, divide by 100. And if I divide both sides by 5.2 over 100, see what that is. What is 5 Newtons divided by, open parenthesis, 5.2 on 100, close parenthesis? 96 is the number on the screen. So I could say K for the green spring scale equals, okay. No, the number is 96. Okay. Can you guys tell me what the unit is attached to that number? 96 what? Ah.
Oh,
Newton per meter. Yeah. Newtons per meter. Right? Hey, newtons per meter. Isn't that like the rise over run of this graph? Right? Rise over run, like the slope. Newton per meter, rise over run. Sure is, isn't it? Okay. So that is the spring constant on this green scale, which is not very stiff. Right? So that's what 96 newtons per meter feels like. Okay. How about the gold scale? Now, do you think the spring constant is going to be a larger number or a smaller number? It's really stiff. Huh. Yeah, larger makes sense, doesn't it? Okay. And on the graph, maybe the green scale is like down here, and the gold scale is like a really steep line, because there's lots of force for even just a little tiny stretch. So here's the green scale, here's the gold scale. Okay. But let's say, so if I stretch this, it maxes out at 50 newtons. Wow, that's like 10 times the force of the green scale. It starts like, wow, there's 50 newtons right there. That's like 5 of these guys worth of weight. And now what is that actual distance? It's actually a little bit different distance. It goes I'm looking at 6.2 centimeters. 6.2 centimeters. A little bit longer. Agree on. So to reach 50 newtons of force, you have to stretch it. Well, it would stretch 6.2 centimeters for that applied force. So 6.2 divided by 100 meters. So what is 50 divided by open parenthesis 6.2 on 100, close parenthesis? That is 806. K is, this is for the gold spring scale. 806 is the number, and then it has the same unit, Newton per meter. 806 newtons per meter. Wow, look at that. The gold spring scale, the gold spring had about 8 times the stiffness of the green spring. All right. We present screen 2, share, flip screen. Oh, okay. Flip back, open presentation, close that, flip back, present. All right, now we're good. Hold on. We did all these. Did that. On the spring, there's the spring scale. Okay, so there you go. Hooke's law, yay. Bottle rocket blasted upward through the air, and there is air drag. Okay, so here's one possibility. Maybe it has some weight pulling down. You think there's a thrust force upward and a drag force also? Okay, so that's one possibility. Now, the diagram that I drew right there, is that rocket in equilibrium? Yes or no? No. You guys see how there's a net force? So isn't that rocket accelerating upward? Not only is it moving upward, it's accelerating upward, right? Because the net force is upward. The net force dominates, it beats these two guys pulling down at it together, doesn't it? Tip to tail. A baseball flying through the sky at 45-degree angle. Somebody just hit a home run. There it goes. Does this baseball have a weight pulling straight down? Yeah. Right? Now, all the projectile problems we did, we've been assuming all along that that's the only force on the baseball. And then that causes it to have a nice parabolic path, right? But if we're now considering air drag, which way do you think the air drag points? There you go, opposite of the motion. And that's the only reason I included the direction of motion, because air drag would oppose that. Do you think you could add those two red vectors tip to tail, and the net force would be like, probably like very much down and a little bit to left, something like that? In fact, that drag force would constantly change direction, wouldn't it? Like if you modeled this in the computer, it'd probably be a fun thing to model. That's always changing.
Is air drag always opposite of velocity?
Yeah, air drag is always, opposite of velocity. Yeah. Like as long as there's no wind and anything crazy like that. 2 people. Hey, it's our donkey friend. Pull on the donkey. You guys know exactly what this is going to be. Tension left, tension right, and ooh, what about this? If the donkey is not moving, there's probably also what kind of force going on? Yeah, like static friction between the hooves and the floor, the hooves and the ground, I should say. Let's say pull this donkey inside doors. So you guys see how the left component of tension or right component of tension are canceling out, but also the 2 forward components exactly balance out with the friction force backward. But you guys know that already. Block on a ramp. I've been preparing you guys for this moment for a long time. This block has a weight acting down. Then I told you guys to introduce a Cartesian system that's oriented to the surface, parallel perpendicular to the surface, to the really light lines. And then break that weight component into, components that are aligned with that new system. It's a parallel perpendicular to the system, cosine sine component. And there are some more forces though, because otherwise that block would just be in free fall. So isn't there a normal force from the surface holding it up? In fact, that free body diagram by itself could describe an air hockey puck sliding without friction down the surface. But that's not exactly the answer to this question. This premise is the block is at rest. So there must be a what kind of force acting? Yeah, static friction. And look at that, isn't that static friction the exact same magnitude as mg sine theta? You guys see that? See that? Let's suppose for a moment that that block is just about to break friction. Like if you had any more force on it, it would break the friction, it would slide down. Can anybody tell me approximately what is the coefficient of static friction? What is that divided by that? pretty close to 1/2. See how friction force is about half of the normal force, right? How about the block is sliding at constant speed down the ramp? At constant speed, is that also equilibrium, just like the last one? Actually, you know what? This free body diagram looks exactly the same as the last one. Right? This is one of those ambiguous situations. Like in this case, this is what kind of friction? Static or kinetic? Yeah, kinetic friction, because it's sliding. Right? And if you knew that, then you would know it would be on the move. Right? But if you did not know what kind of friction it was, if it's static or kinetic, then it would be ambiguous. You would have no idea if that block was actually at rest or sliding down at constant speed, because it could be either one, couldn't it? That looks exactly like the last graph, or last diagram, free body diagram. Right. How about if the block is moving up the ramp and slowing down due to friction by sliding up the ramp? Okay, so it's got a way, break that into components. Notice when I say break into components, really important details to dash those components. If you do it at all on an AP paper, because if you do not dash the components, then AP assumes that you're saying that there are more forces that are acting, which you're not trying to say. You're just trying to recontextualize that weight. There's a normal force, which, did you guys happen to notice that the normal force is exactly equal to mg cosine theta? You guys picked up on that, right? And then, well, if it's sliding kind of up the ramp, then isn't there a friction force kind of down the left, right? Is that block in equilibrium? No, because there's a net force down to the left. That block is slowing down in a hurry, isn't it? We'll say that would for another day. Stop sharing my screen, because that's as far as I've been getting. Call that a wrap.